Okay, so welcome to the session on polynomials and number theory. In this session, we will delve into the fascinating intersection of polynomials and number theory, where we examine the properties of polynomials in the context of whole numbers. We will explore the role of polynomials in solving problems and understanding the behavior of numbers. Whether you are familiar with polynomials or just starting to learn about them, you will find this session to be a stimulating and an informative experience. So sit back, relax, and let's dive into the world of polynomials in number theory. And this was totally not written by me, it was written by ChatGPT, as some of you would have guessed. Okay, so after this not even funny start, so what is this all about? Okay, we all know what polynomials are, right? And yeah, this was the prerequisite, so you should know. We will mostly study polynomials under which have integral coefficients, and we refer to that by this notation. This means the coefficients are integers. Say this is the polynomial. We'll be dealing with polynomials which have these AIs integers. So we will look at a lot of problems and stuff. But first, we'll look at how divisibility works. And I hope everyone knows how it works with numbers in general. So we have this property. If anyone's wondering what this means just means that A minus B divides P of A minus P of B. Okay, so why is this true? Can anyone tell me?
Because the constant term
Sorry, I couldn't hear you.
because the constant term cancel out.
Yes, after you expand the constant term dies and you have something in common, right? Is this clear to everyone?
Yeah.
Fine. Here A and B are integers, so okay, so we want to use this, and this will be useful in problems. First off, let's prove another this is not say a lemma. Prove that f of n divides f of n plus where k is any integer, n is some random integer, f is an integer polynomial. When I say f is an or something is an integer polynomial, I mean that it has integer coefficients. So how do you prove this?
Can I tell?
Yeah, I mean, no, let's wait for someone else.
Also, are you sure you put the K in the right place?
Yes.
Uh-huh.
I mean, look, if you expand, then like, you know what happens. So many theorems. So anyone who has any ideas?
In this we can use divisibility lemon f of n plus kf of n minus f of n.
Can you repeat?
Kf of n will divide f of n plus kf of n minus f of n.
Kf of n will divide.
F of n plus kf of n minus f of n.
And why is that?
By the lemma above.
Like this one.
Yep.
Like, can you elaborate for everyone else?
Um, first of all, your
Like
summing.
what A and B are here? Like,
So basically, A becomes the n plus kf of n, and B becomes n.
right. And what next?
Now, we can omit the k in the divisor, and
Fine.
because if AB divides x, then A divides x and B divides x.
Right. So after, like, you can just like these two get cancelled because like yeah, like it's f of n. And okay, like let me just illustrate in a simpler way. So first, let's prove it for k equals 1. Let's just do what he says. Yeah, like yeah. So it's A and this is B. So we have this. Does everyone follow? Hello, people.
Yes.
Please speak up. And you can write that f of n divides because f of n divides f of n. And you can just extend this argument for like general k, like Arav said. Is this fine? Does anyone have any doubts? Please speak up. You can even do it inductively, like we have this, then so we want to prove it for k equals 2. Now we can do this. Um, Now this is just f of n. And we know this is divisible by f of n, so we can just ignore it. and write this. So you can inductively do this as well. Is it clear to everyone? Can you please repeat the last step? Which step exactly?
Oh, Debayu, this guy is not me. Okay.
Yeah, I know.
Yeah.
Hello. Another Anurag. Okay, I will move on. Next, we will do an IMO problem. Yes. After looking at basic divisibility stuff, we can now kill an IMO problem. So the problem says that, okay, let me just grab the actual statement. Okay, so we have a polynomial of degree n greater than 1, and it has integer coefficients. K is a random positive integer, and q of x is p applied k times to this. We need to prove that there are at most n integers such that q of t equals t. That means there are at most n fixed points. So we will use this notation. This just means that p has been applied k times to x. Is the problem statement clear to everyone?
Yes.
Aditya, Anand, Animika, Anurag. Is it clear?
Yeah, it is.
Okay, cool. So do you have any ideas? I will
Actually,
give
I
you
have done this problem before, so I will not have any comments on this.
fine.
I think we'll have to relate the fixed points of Q with those of P.
You have to relate.
The fixed points of Q with those of P.
How do you know if P has fixed points?
I mean, even if it does, it has at most n such fixed points. That in that way. Basically, we want to prove that Q of x minus x has at most n roots. Real. N integer roots, I mean.
Right.
Do we show that there is only one cycle, like, or like consider x, p square, x, so on, and like if there is one cycle, then do we have to show that it's the only one?
Let's see if it has only one cycle.
Oh, never mind. Probably that. Oh, no, but that might work out. So, like, let's say the cycle, like n is 3 and the cycle length is like 5. That is not possible, right?
No.
Yeah. So, like, if it has a cycle, it can have at max length 3 by the question statement, like if it's true. And maybe we have to show that there can be only one cycle.
Interesting.
I'm not sure if that works.
Yeah, the solution I know like doesn't really use. There might be, like it's likely that there is one. Okay, I will give you people 4 more minutes. Okay, no, 3 more minutes to try
What
this.
if we sort of induct on K?
Okay, so you want to induct on K. Interesting. Why does that make sense?
Because for K
Okay,
is
yeah.
equal to 1, it is
I
obviously
see.
so, and we are not given any hint of what K is, so it makes sense to in. And also, I think that anyways, trying the smaller case K equal to 2 should help.
Okay, so suppose by induction hypothesis we know that like for this K we have only n fixed points. Now how do you move to K plus 1?
So like for I try the K equal to 2 case right now. So if we take K is equal to 2, then P of K minus P of K is divisible by P of K minus K. So every fixed point of so at every point where P of K is P of K is K. Wait, no, this leads to no new information.
Okay, so you're saying P of K minus K divides P of K minus P of K.
Yes.
And then?
If at any point where P of K is not equal to, yeah, this does not work actually.
Fine. It's nice that people are coming up with ideas. But yes, I really want you people to use this property, like A minus B divides P of A minus P of B. Also, this is a P like P5, so it's not super easy or anything. Okay, I will give you a hint. Suppose we have two fixed points A and B. Then A minus B divides. This is by our lemma. But this also divides something else. And what is it?
P of K of A minus P of K of B.
Right.
So PK P minus PK.
Okay, so we have equality.
And this means that P of A minus P of B is either A minus B or B minus A.
We can write it as this, right? Like,
Yes. But now
so
we
how do we move from here?
can probably get some kind of degree bounding contradiction.
Okay, so let's deal with one case. Like we either have this, we won't need degree bounding. Like, yeah, you won't need degree bounding in that sense. Okay, so either this or this is true. Maybe both of them are true.
So
So
what if we like multiply this? So P of A square minus A should be equal to P of B square minus B.
sorry, I didn't follow you. Can you?
So we basically just get that P of A square minus A square equal to P of B square minus B.
Like, wait, wait. Sorry, I had to go for a second. Yeah, so you want to multiply them,
Yes.
but like this means that, but you are assuming that these two are true, right? Like both of them. But
So
then
we
P of
multiply
A
them.
minus P of B is A
Oh,
minus B.
yes, right.
Yeah, that's bad. Also, like say for the sake of contradiction, if you have like n plus one fixed points, why is my lagging?
Okay, then uh, P of X minus X is
Like if you have n plus one fixed points, then like say they are um like they're distinct, right? So we order them like this. Then we have a lot of like things for each pair. And it's really hard to work out every two cases. Okay, suppose it was true that for everything. Okay, let me just say this. We have some, let's pick some AI and AJ. So till now we have this. Right. So suppose this was true. For all ij, for for where I and j are like distinct. What happens if this is true? Like ignore everything else. If this is true for all ij, what goes wrong?
Will it be AI minus AJ?
Yeah, think about it. What goes wrong if this is true for ij? Also, if anyone has any doubts, please speak up or write in the chat. Because this is not an easy problem. Anyone? Vinayak, do you want to say anything? Like something has to go wrong here, right? Like a lot of things. Like if we look intuitively, this is like saying that n degree polynomial, like it looks like q will be an n degree polynomial, and then like it will be. Okay, well, like look at this way. Like it's kind of weird that more than n things satisfy this, right? Because yes, the degree is fixed of p, and q is like dependent of p. So something has to go wrong, and that's why we have this condition that, like, that's why we have to prove that we have at most n. So a lot of these identities following all together should give us some contradiction. Like, what can you think of? Like, there can be something like a parity contradiction, or like, um, yeah, a lot of things can happen. But what looks the most natural?
More than n roots.
Sorry, I didn't hear you.
P of AI minus I is equal to P of AJ minus J for n plus 1 like AIs.
P of AI minus I is why do you have to crash like this? Okay, so P of AI minus I is P of AJ minus J, and then what were you saying?
And this is true for like n plus 1 AIs, like all of those.
Right.
Wasn't it P of AI minus AI? Not
Oh, wait, oops, sorry. I'm so sorry. But I think this was clear, like what I meant.
I guess from here we can show contradiction that there will be n plus 1 roots.
Yeah.
More than n roots.
Right. Does everyone like follow why this happens? Like this is a constant, right? For a lot, like n plus one things. But we have that p is an n degree polynomial, which is bad. And they are all distinct as well. So this suggests that p actually has n plus one roots. And this is bad because p is an n degree polynomial. So yes, this is a contradiction. Okay, we solved the problem. Or did we? We didn't. We had assumed that this is true. So we know that if this is true for all ij, then we will be done. We can force this. Can we force this? Like, can we get rid of all this sign problems? Does anyone have any ideas?
Wait, if we have like a P of AI plus AI and P of AJ plus AJ for n plus 1 things, like all of these, and that should still be a constant, so it doesn't matter.
It does.
Can
That
we
will
do
also be a
something?
contradiction only, right?
What?
Like what she said, like if PAI plus AI is a constant for n plus one term, that is also a contradiction only, right?
But what if
Yeah,
like
I mean, fine. If they are like different things, like somewhere it's plus and somewhere it's minus, then not.
yeah,
If everything
exactly.
is plus, then it's a contradiction only, right?
Yeah, exactly. That's what I'm saying.
Yeah.
You want this to be like stable.
I was thinking like doing it with graph theory. So like if we imagine all the points as nodes, and if we like if we remove the mod for the right hand term, if we remove the mod and a positive signs come, we can connect those 2 points by a blue line, and if a negative sign comes, we can connect them by red line. After that, we might get that 2 points are connected by two lines, both red and blue, and that would be a contradiction.
Okay, so you were connecting, like you're coloring edges which are like positive, like which have
Yes,
this property as red, and those which are like plus, you are
AJ
connecting with,
minus AI. Yes, yes.
and then
After that, I'm trying to show that there will be 2 points at least that are connected by both blue and red edges, because it's transitive also.
okay, okay, that will be a contradiction, right? But how would you do that is the question. I actually have never thought
Involve a
about this.
third thing. Like
Sorry.
suppose you have two things. Okay, no, that's just that. You have PAI minus PAJ equals AI minus AJ. assume that PAJ minus PAK is equals to AJ, AK minus AJ. Like that's the opposite thing.
Okay.
Now AJ minus AJ. Like basically you do some addition or subtraction, I'm lazy to find it, and you find a relation between I and K then.
Yeah.
So basically replace this PAJ by PAI minus AI plus AJ, I guess.
Yeah, this eventually gives a contradiction. You were
Yeah, makes sense.
So is
What
it-
I was saying,
Basically, you can
this,
get a contradiction in graph theoretic sense too. Like there are n vertices and n plus one edges. Like consider that. Then you would find a cycle, and I guess that would give a contradiction of red blue edges. Or either I am clowning. Am
yeah,
I
but how
clowning?
do you like
I was
Like
saying that
it makes sense that, and like a tree has n minus n edges, right? So if there is something more than n minus n edges, then you would
yeah,
get a cycle.
exactly.
Yeah, that cycle would give a contradiction, right?
Yeah, that would be that's a nice interpretation, but how would you get that cycle? Like you do get a cycle actually. You are right, but I'm not sure
Yeah.
like how do you like I think it's much more obvious to go like
Yeah, this way is much more obvious, but like we can interpret it in that way too.
yeah, exactly. Like I think it's much more natural to go
Yeah,
from
yeah, yeah. Like,
algebraic sense to
yeah.
graph theoretic, but I think it's like I don't exactly see how would you go from
Hmm.
the other way.
I see. Okay. This is a nice problem, I guess.
Yeah, but is it clear to everyone? I will summarize this if it is no.
Yes, could you summarize?
Okay, sure. Okay, so I will like okay. So we have our magical property a minus b divides p of a minus b, right? So now suppose we have two fixed points a and b. Then this is true by definition. But we also know that a minus b divides p of a minus p of b. And now p of a minus p of b divides p to the power k of a. This because we are applying p again and again.
Yes.
But this is equal to a minus b. So equality must hold everywhere because if some x divides y, then this is true. But we have equality at the end. So p of a minus p of b is a minus b. Now, for the sake of contradiction, suppose there are n plus 1 points. Right? So, and then you have this for all ij. Now you see that if you could get rid of the signs and just had this, You have this as a constant for like n+1 points. So there is a n degree polynomial which has a root in n+1 points, which is a contradiction because n degree polynomials have n+1 roots
Yes.
and all AIs are distinct. So you want to force this. And to force this, you just simply consider another AK and then just do some algebraic, do some manipulation with get a relation with AI and prove that this can't happen. This is not too hard. Also, you can also like globally sum all of this and like globally sum from 1 to n+1 and see that the sign can't change. So the sign must be always same. And without laws of generality, you can assume that it's positive. And yeah, you will be done. Okay, so what are the takeaways from this problem? First takeaway is that this relation is very useful, super useful. Second is that sometimes, not sometimes, like size stuff is quite important. Like this was people like this probably looked really easy, but this is hard to spot. Like this seems very obvious, right? But I think it's pretty hard to spot, and keeping this very, although trivial yet important size ideas in mind is important. And and the fact that n degree polynomials have n roots at most is in your NCRT, which was a prerequisite. Read NCRT.
I forgot to read mine.
Oh my god. You might be kicked out of the class anytime.
Sorry, please don't kick me.
Okay, we will do another problem about divisibilities. And then we will not study, like, I will tell you stuff about Bézout's theorem. Sounds cool, right? Hopefully it does. Okay, prove that. Wow, the font just became huge. Wait, why am I here? No. Prove that for a polynomial for infinitely many n, mod of P of n is composite. This is not too hard. Like definitely not harder than an IMO P5. So try this problem for a few minutes. Do tell me your ideas.
So I think in this we should assume contradiction. So
Is this not well known? Like any polynomial does not give prime always.
Yeah, this is well known.
Yeah.
So,
So we'll just quote the result and not prove it. We are done. We can move on.
I guess, of course.
Yeah. Okay. I'll stop it.
Thanks.
so in this assume contradiction. So there must be an A such that P of A is equal to P where P is prime. Then
Okay, we assume contradiction, then
there must be some A such that P of A is equal to P with where P is a prime.
P of A equals.
P where P is a prime.
Okay.
now we consider the class P of A comma P of A plus P. We basically consider the class P of A plus KP. So at most, so there are finitely many P's or zeros or minus P's that are contained in P of A plus KP, which means that the rest, all of them should be composite.
Right. So yes, this was the proof. Does everyone get what he said?
Yes.
So basically, if this say P of A is prime, which means P divides P of A. And now this means P divides P of A plus KP. If you are wondering why this is true, this is because of our goated lemma. Like, but I will still just prove it, because why not? But we know that P of A is divisible by P, so P divides P of A plus A plus P. So, and you can inductively move forward to K. I guess it's fine. And this grows. Say P has degree n, unless this is constant. If the polynomial is constant, this is not true, by the way. I should have said this. If it is not constant, this either grows up or down, doesn't matter, because we are considering mod of P of n. And yeah, if this value changes, it can't be P forever and it must be composite.
Wait, so is this sort of like Dirichlet theorem?
Dirichlet says like this is prime infinitely often,
Oh, okay.
like the AP. It's for like degree 1 polynomials. Dirichlet has like a proof which is much harder. Okay.
60 moves.
Wait, you're going to prove Dirichlet in this class?
No.
Oh, sad.
Sad. I thought it was like a good thing.
No, I came here for Dirichlet. You want?
I thought you came here for something else. Anyways, jokes aside, let's move on to how divisions work in polynomials. Yeah, they are normal. You must have studied them in your high school text. Yeah, you have this thing here as well. If you divide p by q, this is called the division algorithm. This is true. And if okay, let me define how GCD works in polynomials. Say you have two polynomials. And note that we are considering integer polynomials here. And key of x is so what's the GCD of this polynomial?
2x minus 1 square into x plus 3 square.
2x minus 1 whole square This, right?
Yes.
So what we do is we plug the factors, just like we plug the irreducible factors. Like look at it this way, like primes where what primes is to normal numbers is irreducible factors to polynomials in some sense. It's not super rigorous, but for now you can look at it this way. So yeah, this is how we factorize this. Yes, so, and if you apply the division algorithm again and again, we had Bézout's theorem for normal numbers. If you have a, b, and GCD of a, b plus 1, then you have x and y such that this is true. Similarly, if you have a polynomial, if you have two polynomials p and q, which have GCD 1, then you can find two other polynomials a and b, such that a plus a times b plus b times q is. You can you can say it's 1, but sometimes you run into problems with the leading coefficient. So you can just say it's c and this is a number. This is not a polynomial.
Why don't you just
And
write
we
it
are
in small
polynomials.
letters?
Huh?
Just write it in small letters then.
Okay, sure. I think k sounds more non-polynomial.
Yeah.
Large scale doesn't sound like a non-polynomial.
It is small k, right?
Yeah, small k sounds like a non-polynomial.
Yeah, so why is this useful? This actually tells us a lot about like the polynomials. First of all, note that this is true for every input of p and q. Like this is true for p of when like this is always true. Like you can find two such polynomials such that this is true.
It is useful because if it were not useful, you wouldn't have included it.
Yeah, exactly. Yes, trivial. Haha, funny. Well, okay. So let's do a problem. Prove that if you have two polynomials p and q, GCD of p and q is 1, then GCD of p of n and q of n is bounded. As in the outputs p and q get, those outputs don't like are small than something. Like they can't just be arbitrarily large.
Why does this remind me of USCM 2022 problem 5?
Can you use it? It's useful in like a lot of problems, a whole lot of problems. Like almost 25 to 30% of int poly, which is a lot. Okay, maybe not that much, but yeah. But at least
Are you convincing me to do the int poly units?
we don't talk about that here, but yeah, fine. Okay, so anyone has any ideas? Ideas, please. Also, by the way, I forgot to tell you, this is also true for rational polynomials, as in polynomials with rational coefficients.
Like, wait, can you scroll up a bit? That AP plus BQ equals to K thing, that is like Bézout's, right?
Yeah, Bézout.
Yeah. So you know that there exists some A comma B such that you can write AP plus BQ equals to some constant,
Yes.
and then you can just scale the things to make P and Q like integers.
I mean, what do you mean by scale them to be integers?
Like,
they are in.
let's just
Okay,
like,
okay. You mean like big enough such that?
no, what I meant is like, what do you say that? If they have rational coefficients, you can just multiply the denominators so that everything is like integer.
Yeah.
Yeah. So you'll have some constant K on the right hand side.
Yeah, that's why I said like two.
Oh, fine. Okay. And now if there is some R which divides both P and Q, it should divide K also.
If there is some R
which divides P and Q both,
yeah,
which means it divides GCD.
yes,
And then R should divide K also, right?
right,
But but K is bounded, so GCD is also bounded.
right. This is the proof. Does everyone get it? Hello.
Yeah.
Okay, I will still summarize it just in case. So if you have some R that divides P of n and Q of n for some n, then this is true. And R divides both of these, which means R divides the LHS, which means R divides K. Now, if the GCD is like, and like GCD of like R divides GCD of P of n and Q of n as well. Why? Why is Miro doing this with me? Yeah, so R divides this too. But if R is if the GCD is unbounded, then R is unbounded as well. But that means that R can just grow bigger than K as K is fixed, which is a contradiction. So GCD must be bounded. This is super important. You should remember this. The proof is also super important, by the way. This size idea is really useful in a lot of problems. Now, another problem of like in the same spirit, if prove that if f of n divides g of n for infinitely many n, f divides g. That is, yeah, we have factors common, like this is polynomial division, while this is like division between two numbers because it is evaluated at n. Does everyone get the problem? I hope you do.
Yes.
I guess I do get the problem.
So assume that f does not divide g, then GCD of f comma g is not f. It is a divisor of f, but not f. So that then we can probably use Bézout on that.
If
I guess there's a simpler way to do this. Like you can consider the Euclid expansion of g of n with respect to f of n, and the remainder should be smaller than f of n, right? That would give a contradiction. Like
yeah,
you
so
can just
you
give
are
the size contradiction. Just pick a large, very large n,
yeah,
that will give a
suppose
contradiction.
yeah, so what you were saying is that if f doesn't divide g, then you can write this say a and b, where b is the remainder, right? And you want to prove that b, and we know that degree of, okay, I should use capital, right? This is just absurd.
Wait, you messed it. Like you
Oh, okay.
misplaced g and f, right? Oh, okay.
Happens.
Yeah, no problem.
We know this is true. Uh, so we have this information, and we probably somehow want to force that this is not true.
Also, shouldn't it be degree f instead of degree a?
Sorry.
No problem.
Okay. So, any ideas?
Now consider the thing g minus f of a.
Okay.
It is always divisible by means like it is divisible by f for infinitely many values of n, right?
Yes.
Pick a really large n. Pick a really large n. I guess that would give a contradiction.
Yes, that forces n to divide v.
Yeah.
And yeah, this is a degree contradiction basically.
Yes.
I hope everyone gets his reasoning. Anyways, I will
Or
repeat.
you can just like see polynomials with higher degree grow faster than the polynomials with
Yeah,
slower.
exactly.
Yeah.
That's the idea.
Yes.
Size in general is like super useful. Wait, I'll be back in like 30 seconds. Okay, so as Anurag said, you can just make this arbitrarily large and get a contradiction. But here's a neater way to like, it's the same argument, I will just say. Yeah. So we have this. Now for some n, this is true. Now since f of n, and we are picking n such that it is among those infinitely many n's such that f of n divides g of n. This and yeah, and g of n can be written as x times f of n because f of n divides g of n. But this means that f of n divides b of n. And this is true for infinitely many n. Does everyone follow?
Yes.
Okay. But we know that degree of f is larger and it grows much faster. But we know that if a divides b, then a is less than or equal to b, which is false because f grows much faster than b. So this can't be true, and yes, fs has to divide g. Okay, this is one of the few questions we should ask ourselves when we are doing a polynomial problem. Okay, so let's ask some questions. Like in similar spirit. Suppose we have two polynomials. We won't necessarily prove it, but yeah, let's just see. Like suppose we have two polynomials thinking. We are just experimenting, okay? And they have like every prime that, okay, like say if some prime p divides p, like this is true. P divides the polynomial p if and only if p divides, which means both of them have the same prime set. They have the same set of primes dividing each other themselves. So what can you like say about this polynomials? Anyone?
Basically, they are congruent modulo p.
I mean, for like, this is true for every prime p.
Does this mean that the p-adic evaluation of p divides the p-adic evaluation of q? Actually, I mean they're both equal since they both divide each other.
Um, if nu p of like, so you were saying the exponents of stuff is equal, right? Like if for some n. Okay, what exactly are you saying?
That we take p mod we take the polynomial p mod the prime p and the polynomial q mod the prime q, and I claim that they both are equal.
Like I'm like, this is true for all the primes. It's not just one prime.
Oh, okay.
Like they have the same prime sets.
That means that we p and q are probably supposed to be like equal.
Yeah, p and q are probably equal. That seems natural.
Oh wait, p divides that. This means that for any prime p divides the k that we use in the polynomial Bézout. K should be within taking a prime large enough.
We can't Bézout here, right? Because GCD is not one, of course.
Oh.
Like it might not be one. It's most probably not one because we have that stuff divides each other.
But then we can handle it some other way, like take the GCD of p and q to be r, then yes, in some way shape or form.
Maybe use Euclid expansion again.
How exactly?
And then take a large prime p that divides p and q.
Like,
Like,
what are you trying to prove? Are you trying to prove these two are equal?
yeah.
Okay.
So like consider without loss of generality, consider the degree of p is greater than degree of q.
Fine.
Then you can do the
But
Euclid
it's
expansion.
equal.
Oh, we will ignore that case because I want to. Then use the Euclid
Okay.
expansion.
So
Yeah.
P equals AQ plus B.
Yeah, yeah. And then take a really large prime p that divides p.
Yeah.
That should divide b too, right?
Right.
That would give a chain of like
Okay,
things.
wait, not right.
Why?
Because P divides P of n doesn't imply Q divides P of n.
Oh,
It
like a.
divides it at some point. Yeah.
Okay,
We
okay,
don't have this here.
okay, okay. Then
Yeah, think about it. Like even I don't know the answer. Okay, I do know it, but like
so like
yeah,
we are live solving it right now.
yeah, classes should be like
Yes.
yeah, let's just ask
That's
questions. We should be able to answer. Like it seems fairly natural that these two should be the same polynomials because primes behave weirdly. Any other ideas?
but your voice is cracking.
My voice is cracking.
No, it's fine now, I guess. It was cracking.
I guess I'm cracked.
Yeah, that's why your voice is also cracked.
Yeah, jokes aside, do people have ideas? Do tell if you like Yeah, just share your ideas. We are here to do that.
Wait, but can't you make like P and Q be divisible by same prime for some value of n? Like it's pretty easy to do that, right?
What?
Like can't you make P and Q be divisible by the same prime for a fixed value of n?
P and Q divisible by a fixed prime. Can you necessarily force it?
Like take a large prime P that divides P of x. You can find infinitely many x that such that P divides P of x, right? That makes sense.
I didn't follow you. Can you repeat?
Okay, okay. So like if we find one x such that a prime P divides P, we can find infinitely many x's that prime will divide P for that value of x.
Can you? Yes, you can.
Yeah. And same holds for Q, right? Like if we find a point where like P divides P, we can also find a point where P divides Q.
Hmm. But the problem is you can't necessarily find one such one.
Yeah. I see.
Okay, so we are really missing Bézouts, right? Okay, so here is a short digression on what irreducible polynomials and minimal polynomials are. Okay, before that, let's just, if some prime is not like, say some q divides q of z, and we need to realize that the thing Anurag says doesn't work, because that prime can just like, this q just might be something in the leading coefficient. Like if p is of the form c times p dash for some leading coefficient c, then like p dash might just not output q every time, right? Like it might just never output this like prime, like a number that is divisible by this prime, and it might just happen that um, q divides c, and that assists it to like satisfy the condition. Do people follow? So actually this is like, if you have a large enough leading coefficient, then you can actually make some conclusions about this, because then you can do the Euclidean algorithm thing. Because like if some large prime q divides this, and this is also large enough such that q divides c,
Well, but
then
then
we
like
have,
actually this contradicts our equal assumption, because then we can take the polynomials x square
yeah,
plus x
this
up to
does
x square
contradict
plus
our,
x.
like we have never assumed it's equal, right? Like we were trying to prove it's equal, which it is like, which is probably not true.
Yeah.
But okay, so do people know what irreducible polynomials are?
Yeah.
Yeah, so they are basically polynomials which you can't factor in, can't factor into two or more polynomials which have integer, like for now, like we are talking about irreducibility in like z of x. So if you have, say, polynomial x squared plus 1, you can factor it like this. But like,
Now it's us four only, right? हम चार ही हैं अब बस.
well, but I is not like an integer. So x squared plus 1 is actually irreducible in integers. So, and we have this thing called minimal polynomials. So what are them? Like, suppose you have some number 2, and this holds for like, we might pick non-integers as well. Say we have 2. What's the polynomial with least degree, which has a root 2? It's x minus 2, right? You can't have a 0 degree polynomial. Like, so this is the minimal polynomial of 2. Also, we are like ignoring leading coefficient because obviously it becomes bad. Similarly for I, the minimal polynomial is like x squared plus 1. And notice that I has its conjugate minus I as well. It can't exist independently. And that's why the degree is 2. And I and minus I are called Galoff conjugates. So basically minimal polynomials and irreducible polynomials go hand in hand. They are almost equivalent. Like x minus 2 is irreducible, and it is like, it is the minimal polynomial. It is a minimal polynomial. But you might similarly here x squared plus 1 is irreducible and it is a minimal polynomial. So they're almost like equivalent. This is quite useful. So what if in our exam, like in our question, P and Q were irreducible? Then notice that if two polynomials are irreducible, this implies that GCD of PQ is 1.
I mean, then you can use Bézout easily.
There, what?
Ignore. Just ignore.
Fine. Okay, so I hope this is clear why the GCD is like 1. This is simply because in irreducible polynomials, first of all, we ignore the leading coefficient. And if like we have if we have common factors, then it is not the minimal polynomial in the first, like it is not irreducible in the first place. So GCD of P and Q is 1. And now you can use Bézout. That is exist A and B such that is true. Now, if you have the same prime set, now just say the magic word or the magic sentence, please.
Take a large prime P such that.
Yeah. That's what you do. Or do you? You still don't have a fixed point, right?
But you can force a fixed point, right?
And how?
I'll need to think about this, but maybe we can. I think
Yeah,
so.
this is not as obvious as it seems.
I think so.
What's the question?
The
Like,
question is, you have polynomials P and Q are irreducible,
Mhm.
and they have the same prime sets.
Okay.
Like if, like
Yeah, I got
this
what that
condition.
means. What do you know?
Hmm?
What do you need to prove?
We need to prove we are just experimenting what we can do. Like it's a natural claim that P and Q might be the same thing.
Ah.
But can we do that? Like of course, if you have this Bézout setup and you can find a fixed point, then you can pick large things, like a large fixed point, then you can pick a large thing such that it exceeds K.
Mhm.
But can you do that?
like consider a prime P that divides P for P of A1 and divides Q for Q of A2.
P divides P of A1 and P divides P of Q.
Q of A2. A2. Like if A1 and A2 are congruent modulo prime, then you're done. You can easily find a fixed point.
Um.
Because like
Okay.
A2 would be of the
Yeah.
form A1 plus PK or something.
Yeah.
Yeah. Now we need to find such A1 and A2.
So you want A2 to be
Congruent modulo A1. Congruent to A1 modulo P.
Wait, but how did we get that P and Q are irreducible?
We are assuming they are.
Hmm.
what are we assuming? Okay, we want this to happen.
Yeah.
Nice. But this might just be not possible to force.
Yeah. Like this is just wishful thinking.
Yeah,
That's
this
all.
is wishful thinking, yeah. But this is quite useful. Like that's what you do when you like run into a random wild problem, right?
Yeah, but like sometimes wishful thinking is just too costly.
Yeah, but yeah, it's nice. Okay, okay, this seems hard. What if we like modify the question? Like let's ask another question which is like related. Um, say for all n, say for like all sufficiently large n, f of n and g of n have the same prime set.
You can easily force them to be equal.
How?
Okay, so like, wait,
Here we don't have the irreducible. Like, okay, we do.
like even if you don't have it reducible, like if you do have it reducible, they have to be equal clearly.
I mean, the point of irreducibility is so that we can reduce it to Bézouts.
Yeah,
Or we can just say probably like GCDF and G is one. But like irreducible, like irreducible is nice because like you can form every polynomial with like um like with multiplying irreducible polynomials, and we will see in future how it is useful as well.
Hmm.
Wait, which problem are we doing again?
Oh, this is a new question, which is like for all large n, we have that f of n and g of n have the same prime set, and f of n and f and g are irreducible. So what conclusions can we make? Can we make the f equals g conclusion here?
Same primes.
What?
What do you mean the same primes? You mean the
Uh,
same prime divisors?
like say f of n is 38.
What if g of n is say f of n square? Oh wait, no, we
But
can't use.
then, like, f of n is irreducible, right?
Yeah,
So then, like, it
Exactly.
can't happen. Yeah. Like, you can consider the Bézout's form of
yes,
this
yes.
f af plus bg is equal to some fixed constant k.
Okay.
So, like, for large n, we can have that modulus of f and modulus of g are divided by some very large prime p.
For
Or b.
large
No,
n.
no, 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 no. Just ignore it. Like, can we force f and
Yeah,
g to be?
you can do this here. Like
Wait,
pick
but then that means that this prime set is itself bounded to some things since k is finite.
But it can't be bounded, right? Because of irreducibility.
okay, so let's do what Anurag said at first. We pick large n. We pick large n, and um this is true.
But then said prime set has to be divisor of k.
Yeah, but like picking large n does give you large primes, but it doesn't like imply that f of n will have large primes as well, because f of n can be something like 2 to the power 99999 as it grows.
Yeah, but we will try to prove this that the set of primes dividing f and g are not bounded. Can we do
Yes,
this?
and this is just the fact that
They
polynomials.
both are irreducible, right? If they both are irreducible, they can't have this. They can't have a bounded set of factors.
um yeah,
So I
so
guess
I don't see why that is true.
this just reduces to the fact that polynomials have infinitely many primes dividing them. Do you see how?
yes, I guess. Say like there are finite. Say there are some finite amount of there is a finite set of primes that divides the
Okay,
polynomial p.
we will prove like the fact later, but like, can you see how it gets reduced to this?
Yeah, yeah, I can see.
It's simply because like,
Because like then you will get some large prime p, and that will give a contradiction.
yeah. So basically, you pick large n such that f of n has a large prime divisor, which means g of n also has a big prime dividing it, which means big prime divides k, which is contradiction, right?
Yeah,
Yeah.
but
But
why do polynomials have infinitely many primes dividing it?
yes, that's the question we will answer now. Do polynomials actually have this property?
But I need to go for 10 minutes. Bye.
That means it's only us two for the next 10 minutes, which is very huge.
You three guys, not us two.
Well, I think we don't have too much time left as well. So
So I will wait only then. Like, we. Okay, I'll wait then.
so now let's see. Pranav, how much time do we have?
Minus 15 minutes. It was supposed to be till 3 or 5. But if you want to extend, maybe like 10 minutes.
Fine.
Yeah.
So from chasing one question to another, we have run into this question. But how do we prove this? Help. We have been chasing for random properties. We went from this and reduced it to when P and Q are irreducible so that Bézout would work, but then it doesn't work. And then we weakened our condition to this, that they have the same like prime set for individual inputs. And now we have this question. This is traumatic, but yet nice.
Just like IMO 2017 problem 5.
Wow. Okay, that problem is nice.
But
It's
traumatic.
magic actually.
The most dramatic problem to yet exist is 2018 C5. It has given nightmares to everyone.
No.
Yeah, fine. But let's answer this now. Okay, so good news to all of you. I know the proof to this. And humans know proof to this in general. So
What
we
is it?
finally
Can't we
something.
say it's well known and move on? Like, that's the tool we mathematicians use. It's trivial. Move on.
It's actually well known. It's called Schur's theorem, and some people call it Schur's.
Yeah, Sanjana covered it in her
Kurt's
class.
theorem.
But it's not Schur's, it's Schur's.
I know we need to assure himself.
So Schur's theorem says that this is true. Yes. But how do we prove it?
Wait, let me copy paste from Sanjana's handout.
No. Why?
The theorem, that is it.
Okay, so do people know the proof that there are infinitely many primes and not like primes?
Like, we need to go by contradiction, right? That's the only way.
Yeah, the Euclid's proof.
Yeah.
Euclid's proof is like if you have if there are like finite number of primes and the set of those finite primes is this.
Then just take a number that is not divisible by any of these primes.
Yeah, like just take this.
Yeah. We can interpret it in polynomials then.
Take P of this, you mean?
No, these are primes. Like we are like this is the proof that there are infinitely many primes in general.
Like Euclid used this
If there are
proof.
finitely many primes, then just pick this. This is not divisible by any of these primes, so this is a prime.
So is a dependent variable in the polynomial.
What?
What do you mean pick this?
Like, we are just proving that there are
Ignore
infinite.
the polynomials. I'm talking about the proof that
Yes,
there
yes.
are infinitely many primes in general.
Understand.
Yes, so do you get it?
Okay, now so basically what happens is that we take in the polynomial, we take a prime whose for the number that is the dependent variable. So basically p of x, we take x whose VP is greater than the VP of the constant term for all the primes that are dividing this polynomial.
For
No, wait, could you give me access to the
yeah,
annotate on?
how do you give it?
I got it anyways. So basically what I'm saying is that if you have P of x, then the constant term C and the finitely many primes that divided that are P1 up to Pk.
What's the constant C for?
The constant term of this polynomial.
Okay.
So now what happens is that if we take x such that x large enough, such that a large enough power of each of these primes divides x, which is obviously greater than the highest power that divides c, then p should be way larger than x, but its its prime power should be less than x for each of these finite primes. So another prime needs to divide it.
Okay, so the idea is correct. What is a number which has this like large VP?
Wait, I have another idea as well.
Okay, sure.
So like let a1, a2 dot 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 ak be the points where p of x is divisible by p1 dot 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 pq respectively.
Okay.
So now like you will construct an x such that p of x is divisible by all of these primes.
Okay, CRT.
Yep. And then we will just like get find a value of, you find a value of this polynomial which is relatively prime to that p of x,
Okay.
and that will do the proof.
Okay, so wait, why am I annotating? Um,
Now like with CRT you can guarantee an x such that all of these prime divides p of x.
okay, you have this. Wait a second.
Wait, Aru, can you erase your notation? Okay, you can.
Right.
Wait, he did, no problem.
Okay.
Okay, so what do you do after this?
You can construct an x such that all of these prime divides p of x.
Can you?
Yeah,
Like,
we can. By CRT you can.
yeah.
Now we need to just find a value of this polynomial that is relatively prime to this p of x.
Yeah, but that's the hard part.
Yeah.
I thought like, oh my god, this guy has found a groundbreaking proof of Schur's theorem.
I do a lot of visual thinking.
Yeah, nice. Okay. Okay, so Arav's idea was similar to like, yeah, so we keep in mind Euclid's proof. Yes, we still think of stuff that a man who was born 2000 years back did. So really says about our progress. And yeah, so we consider f of n factorial. This makes sense, right? Because this covers lot of primes. Similarly, this is similar to P1 till Pk. Right?
Oh yeah, then it would be relatively prime to all of these p1 dot pk.
No.
Like if the constant term is greater than 0, then yes. If
Um,
that constant term is not p1 or something.
okay, let's see what happens if. Okay, first look, this is this, right?
Yeah.
Constant term of poly. Okay, now what do you do? Anurag.
Now, like if this constant term is divisible by these primes, then we are in a really painful condition. But if it isn't, then it is like clear why f of n factorial would be relatively prime to p1
We are in
dot.
the painful conditions, sadly.
Yeah. Okay.
Yeah, and this is f of 1, f of 0. Okay, let's see what happens if f of 0 is 1. Okay, so if f of 0 is 1, what happens? F of n factorial is 1 modulo n factorial, right? Hello.
Yeah, then you're done because like then you can find the and
Yeah.
yes.
So if f of 0 is 1, this it is nice. So when f of 0 is not 1, we want to force f of 0 to be 1. But how is this possible?
You can consider the polynomial f of n factorial minus c minus 1.
What?
Yeah.
No,
Consider the,
repeat.
consider the polynomial f of n factorial minus c plus 1. If
Okay.
this polynomial had if this polynomial had infinite finite amount of primes dividing it, it would be a contradiction.
If it would have. Yeah.
Yes, so you're done, I guess.
No, right.
Why?
Because like look, this is
Okay, like now.
this constant term can be really bad.
Mhm. So like now take n factorial such that like this f of n factorial will be divisible by n factorial. Wait, no.
Okay, so what if f of 0 is 0?
You can just like take any prime and
Yeah.
enjoy.
F of 0 equals 0 is clear, right? Because
Yeah.
then n divides f of n always. Okay, so we ignore this case and do the magic substitution.
Wait, I got the idea. Like if C is divisible by any of these primes, P1 dot Pk.
Huh.
Now take n x such that x is equal to these primes multiplied by some m factorial.
Okay.
Now you can take that these primes like you can take these primes out and get something of the form f of m factorial is congruent to something that is relatively prime to all of these primes mod something. That would do this.
Now,
Wait, am I wrong again? I am wrong again.
sympathy from here. Okay, so we do the magic substitution. This forces G to have like this forces G of 0 equals 1. Do you see why?
Yes.
And now you apply this to this. This means G has infinitely many primes. F of 0 is a constant, so F2 has infinitely many primes.
Very good.
How nice is that?
Probably the same idea I had, but okay. I'm such a noob in execution.
Execution is hard.
Yeah.
Okay, so I think I will end this class with this. And I wanted to discuss a few more problems, but we don't really have time. And if you want to do some problems, then yeah, try these. Try this one. This is nice. And then you can try Canada 2010, I think. Yeah, 2010 P5. Also, you have okay, not this one. Okay, for now, just do these two problems. These two are nice problems. If you like need any more problems, like this will keep you busy for some time. And if you need more problems, then you can just DM me on Discord or something, or ask me on the server.
Okay.
And yeah, if we have a part 2, then I will cover more stuff. Like we will ask more questions. Like what happens if a polynomial is always a perfect power? Or what happens if for large enough and two polynomials have the same, say, what can we say? Same range, like same output values. Like it looks like it seems they should be equal, but we have to prove it. And we just might not be able to prove it like this one. So yeah, this is quite interesting. So I hope you enjoyed this class.
I did enjoy this class to every bit of my existence.
Wow. Okay, okay, we can stop recording.
अंदर जी सर कब करेगा?
First, let him stop recording. I don't want our personal statements to be leaked on YouTube.
हाँ ठीक है.
Um,
Debayu Chakrabarti is the host now. Pranav Chaudhary is the host now.
You know it, and